গল্প করতে ভিডিও করি।
كذلك بتحدد لازم يكون تكلم الآن حضرتك. Good morning. أيوة. هذا التست حقك. Can you hear me? Mr. Ramzan?
Yes, we can.
Okay. Bismillah ar-Rahman ar-Rahim. We will start our first session titled by First Session Farming with Autonomous Drones, Real-Time Data and Efficient Fertilization Techniques. The authors, Mr. Madul Shihab, Rafsan Shaheen, Arnab, and Shajib Hussein and Abdul Shufan. You can start. Hello? You can. You're muted. I can ask to unmute. Mr. Rasman? Hello?
Assalamu alaikum, ma'am. Can you hear me?
Yes, we can hear you.
Oh, ma'am, due to some networking issue, the presentations are not opening. Can you give me a few minutes?
Excuse me? Do you need a few minutes?
A few minutes, network issue there is.
I can't hear you well. They have technical issues. Yeah, we can share. Yes? Mr. Rafsan?
Assalamu alaikum, ma'am. Can you hear me?
Yes, I can hear you now.
Sorry for my inconvenience.
Would you please, requesting for multiple yes. Would you please share your presentation?
Yes, ma'am.
You can start.
Assalamu alaikum, everybody. I am Rafsan Jani, and welcome to our presentation. Our topic is PCS farming with autonomous drone with real-time data and fertilization technique. And these are co-authors. And this is our presentation outline.
Mr. Rafsan?
Yes, for background studies indicate autonomous drone developed for PCS farming using technologies such as Raspberry Pi, and we use CNN and YOLO 4. We should change productivity in agriculture, and also drone minimize chemical and accuracy distributed fertilizers, which increase efficiency and decrease environmental effect. PCS farming uses systems such as GPS and multiplex sensor and artificial intelligence for effective results management. It also allows sustainable agriculture to balancing product with conversion. And our objective of this design an AI operate autonomous drone system for real-time monitoring and agriculture and fertilization with target and application accuracy higher than 90%, thereby minimizing wastage and optimizing resource use and ensuring that the system contribution are sustainable through targeted fertilizer application. The eventual task will be validating the efficiency, stability, and effectiveness of the drone in real field agriculture. And research gap. Agriculture research has indicated multiple gap in current fertilization practice, indicating being to be high PCS drone fertilization in developing few area. In addition, most current systems do not fulfill utilizing robust AI prediction and prescribe models such as CNN and YOLO for real-time discussion. Existing technology of UAV for owning the restriction in payload. Also accuracy, field coverage efficiency, as well as not addressing the environmental consequences associated with wastage and over application of fertilizer. And research contribution of the our research come up with such advanced system design and could fertilize the uses and superior technology such as Raspberry Pi, GPS, and AI. And system noted 98.3% inclusive or of our fertilizer application. Beside, the solution has been validated in real field site that tested the drone performance in 60-meter square cropland area and delivering maximum output with a 50-gram payload in 50-gram payload at 28 kilometer per hour. These are methodology. We use the deep learning based drone assist PCS drone assist agriculture system, and it mainly consists of fertilization tank and spare system section. Those flowing accuracy, field data collection and clean experiment data analysis and further data processing and transfer for sending analysis. This model update data accurate on all state and ensure real-time update. The drone application work under structure control system, allowing the capture and process data accurate and reliable. And these are CNN structure and YOLO 4 structure. Yes, CNN structure, despite the architecture of convolution network, convolution neural network, which is CNN, it has been designed as a multi-layer structure with input layer and convolution and max pooling layer. Density incorrect and neurons and output layer to process image for analysis. And figure 3 indicate the structure of YOLO 4. It's a compact version of YOLO model. In fact, it analyzes image through several layers. The combination CNN and YOLO 10 YOLO 4 ensure high density for feature detection of agriculture and real-time decision making for operation by drone. And this is the structure of YOLO 4 and Copland Inspire of our project. And this is the methodology. It starts with the pre-flight check of all elements. Also, in case any problem, the drone switch to manual mode of land and operational, depending on GPS. A flight path is loading right before takeoff. Then the drone stabilizes and resets the field. And at this point, the drone applies fertilizer, and at this time, the CNN model is used to monitor the field. When it is done, it checks the battery and also no neither running for operation in or field back to the base and base section in case of battery insufficient. This is the impact of our project. Our control structure of the project. If any failure occur, the drone goes to manual mode and landing. Once everything is operational, flight path land from GPS and drone take off, stabilize and goes to field. Here you see the 4 step of our drone working. And these are drone specification. We use GPS module, motor controller, Raspberry Pi, and octa-coupler farm, and battery, and propeller, and brushless motor. And this table presents the drone performance matrix of agriculture spreading across the 4 tests. Test 1 show drone applied fertilizer with 97% accuracy, covering 58 meter square of land at a speed of 35 km per hour and payload of 100 gram. Test 2 approved accuracy 97.8 with slightly higher payload between 250 gram and nozzle size of 140 micrometer. Test 3 achieved the higher accuracy 98.3 with 500 payload and nozzle size of 75 micrometer and covering 59 meter square of land. Test for payload of 750 gram and nozzle size is 120 micrometer and show slightly drop to accuracy of 96.2 but still cover 57.8 meter square. This graph incident between payload and flight time and the fertilization of a cover by drone as a payload increase in 100 to 750 to and the flight time also increase from 0 to from 3.09 minute to 4.92 minute. However, we observed that the fertilization area covered 59 meters square and 500 gram payload in test 3 before decreasing slightly with higher payload of test 4. The graph highlight the balance between payload, flight efficiency and coverage area. This, this table compared the performance of our study is previous work in drone-based agricultural sparing, and in test 3 our drone using 75 micrometer nozzle and 500 gram payload, achieving 98.3 accuracy with 1 meter square missed location. Compared to a previous study, our work show superior accuracy with smaller nozzle size and moderate payload. And also study 1, a smart aerial agriculture or UV fertilization process use large nozzle and heavier payload but achieving slightly lower accuracy. And study 3 demonstrated similar accuracy but with a large payload with higher speed. The autonomous fertilization drone system show excellent operation reliability with at 90%, 95%. It also achieving a application accuracy of 98%. Fertilization also GPS guided navigation and real-time monitoring allow for efficiency coverage of 959 meter square per flight, and the image processing and object detection capability are most accurate with the navigation of 310 euro. For future work, future development are to improve the autonomous fertilization drone and concerning with facility and decision making by AI and multi-spectrum imaging for solar charging and IoT integration. And however, financial discussion and developing countries the challenge of wide adoption. This is the reference we use in our paper, and thank you for.
Thank you, sir, for your presentation. Is there any question from the audience?
What sort of flight time could you get on your missions? I'm kind of curious about that. How long would the battery last?
Sorry, sir, I did not understand.
What sort of flight time could you get out of the batteries you were using? How long could the flights last? Sorry.
Sir, flying time, sir, you asked for.
Can you repeat
It's
the question?
30.
Yeah, okay. Can you write the question on the chat, if you don't mind?
Sure.
It's 30 minutes. We test in every time.
The question is, how long could the flights last?
The maximum flight time is 30 minutes, and we test in every time. It's almost around 30 minutes.
Can you almost what, Mr. Rafsan?
7 to 13 around.
Weight of our drone.
Thank you.
Is
Are there any questions? اتفضل يا دكتور. Yeah, there's a question from the audience here.
Yes, please, Ms. Rafsan, Mr. Rafsan, could you tell
yes.
us about the missed area in terms of performance? I noticed that your number is higher than similar works in the area in terms of missed area, similar work, I mean, in the literature. So, could you justify why you have more?
We use a 60 meters square area.
We used in our project, we used only 60-meter square area. That's why it precise before our demonstrating or taking result in 60-meter area is a very low for a research purpose. When we take the more area, then the accuracy may be decrease. But for a small area, it can accurate for 98%, 90 to 98%.
Okay, thank you.
Okay. Are there any more questions? Okay, thank you, Mr. Rafsan, for your presentation. And we can shift to the other presentation. Thank you.
Thank you, ma'am. Assalamu alaikum.
practical for real world application.
Hello, can I start my presentation?
Yes, we're waiting for the presenter to come and then we will start. Hello? Marine, are you gonna present your presentation?
Hello, ma'am.
Marine Abda?
Uh, can I present my presentation? Paper
Yes.
ID 168.
Okay. We will start your presentation, autonomous parking valet system, path
Yes, ma'am.
planning and control in complex environments.
Yes, ma'am.
Presented by Islam Hussein, Marin Allah, Manuel Khan, Asfer Rahman, Abdul Sufyan, and Rahman Tijan.
Yes, ma'am. Should I start?
Yes, please, can you share your presentation?
I am sharing my screen. Can you see it?
I cannot see your presentation. Can you stop sharing and start sharing again?
Okay, ma'am. I'm trying. Now, ma'am. Is it visible?
Okay.
Should I start, ma'am?
Can you share your presentation again?
Okay, ma'am.
Try again. Yes.
Now, ma'am. Is it visible?
Yes, it's visible.
Okay,
You
ma'am.
can start.
Assalamu alaikum, ma'am. I'm Maranul Alam, and now I'm going to give a presentation on autonomous parking valet system, path planning, and control in a complex environment. So I'm Maranul Alam, and there is my co-authors, and our paper ID is 168. So this is our presentation outline. I'm discussing one by one. So background. So, significant progress in autonomous driving technology enables vehicles to execute complex tasks with a minimal human input. And it is designed to navigate vehicle available parking spaces in structured environment, likewise a parking lot. And here we have used path planning algorithms like A-star algorithm and RRT planner. It can say rapidly exploring random tree planner algorithm for the minimal path planning. So, introduction. So there are some research gap in our research paper. Most of the APV system, automated parking valet systems, focuses on the static environment. So it has limited ability to handle any dynamic obstacle or problems. And the current solution are mainly tested on control parking environment as it lacks robustness in scalability in urban environments like complex urban parking systems and real-time SLAM integration. There are gap in incorporating real-time SLAM. It means simultaneous localization and mapping, continuous update problems. So our research contributes like it has designed a comprehensive framework for autonomous parking, simulating parking in a controlled environment. And we have combined the hybrid A-star algorithm for path planning and time elastic band algorithm for the real-time trajectory generation. And for precise vehicle control, we have used Stanley lateral control, and we have achieved the vehicle movement properly. So we have demonstrated the system efficiency and collision avoidance through the simulation. So path planning and behavioral layer. So system overview, we can see we have mainly combined three layers. stationary obstacle, road markings, and park cards in a single layer. And combined layer is acting as the coast map of our proposed system. So global and local path planning. In figure 3, you can see the A-star planner is determining the optimal path through the structured environment. And figure 4, you can see the real-time adjustment is made by the local motion planning, which is also involved with the A-star planner algorithm. And moving to figure 5, we can see that hybrid A-star algorithm is determining some multiple paths, and it is detecting the smoother path for the navigation system. So full path execution and behavioral planning. So you can see in picture A car is entering in a parking lot, which is the structured parking lot in this scenario. And in picture B, you can see the car is navigating through the waypoint. And in picture C, you can see the real-time local path updates are being made. And in picture D, you can see final parking maneuver is going to happen. So result analysis, we can see for parking maneuver, figure 7 analyzes the single bounding shape around the vehicle, which can detect any kind of collision. And for better accuracy, in figure 8, we can use a new collision checker system where some overlapping circles are using for better accuracy. And for figure 9, we can see the improved obstacle detection and safe navigation through a coast map. So another result analysis is the figure 10, which illustrate parking maneuver using RRT planner algorithm. And parking maneuver, lastly, we can see the figure 11, a car is getting parked in a desired position, and in figure 12, it is the initial approach for parking, and rate shifts path planning method for reverse parking. So conclusion, as we develop a APV system that is autonomously navigating and parking in a semi-structured environment using advanced path planning technique, and it is mainly achieved by hybrid A-star and RRT planner algorithm, and it is giving comfort to the passenger by enhancing the spline-based path smoothing. And in future, we can work with the dynamic environments and other research gap in our paper. So this is the references we have used for the paper, and thank you. That's from my side. Do you have any question regarding this?
Thank you, Mr. Allam. Is there a question from the audience? Okay, I have a question.
Yes, ma'am.
Do you consider the parallel parking in your model?
No, ma'am. I have considered a semi-structured model, MATLAB-based simulation.
Oh,
Yes, sir.
is there any question in the tutorial? Any question? Thank you, Mr. Allam. Thank you so much for your presentation.
Thank you, ma'am. Assalamu alaikum.
Dr. Ibrahim?
Okay, so thank you, Mr. Mali. We will close this session and then we will move to session 2 with new set of presenters and topic. Okay, so thank you for joining us.
It's you will start from here. Okay. You have a flash or something like that? Okay. You can come in my place.
Fine, okay.
Keep it in the middle.